want to tell you about Gordon, which is a real interesting collaboration between the San Diego Supercomputer Center, Appro, and also SC'11 systems. And a couple of years ago, we got an assignment from National Science Foundation to envision a data-intensive computer. We didn't really get a whole lot more guidance than that. They wanted us to, to think outside of the box and think, what should a data-intensive computer do? I mean, I guess it should handle big data and do it fast, right? And we looked at a bunch of different options. But and by the way, I'm Alan. I'm the co-PI, and Mike Norman is the principal investigator. He's the director of SDSC. Thought he might be in the crowd here somewhere, but maybe not. What we came up with, what is a data-intensive computer? Well, we thought it's something that emphasizes capacity and memory over flops, and it also perhaps emphasizes I/O operations per second over floating point operations per second. We've got this neat thing called the top 500 list, and that, in fact, ranks systems basically on their ability to do floating point operations per second. Doesn't tell you much about its capacity, doesn't tell you much about its ability to do I/O. Well, as of about a week ago, we have the number 48 system on the top 500 list and the number 1 system on the I/O ops in the world. We're doing 35 million I/O ops per second. The last year's record was 4 million, so we've blown that record away. And we're only, we're only doing about 280 teraflops, which maybe isn't enough for some people. But what we essentially have is a more balanced system, we like to claim, in terms of ratio of I/O capacity to flops. And of course, it's going to depend on your application, which of these things is more important to you. But for many of the application domains that we're looking at in medicine and social science and data mining, then this is the right kind of balance that these applications need. The system's actually shipping tomorrow, so it's very exciting. I'm up here at SC, but it's shipping from SC'11 in the Bay Area down to San Diego. Already been burned in down at SC'11, and that's where we set the top 500 and the I/O ops numbers, moving it down to San Diego tomorrow. Hope all goes well with that. Well, let me skip ahead a little bit. How did we do it? Well, we did it in a few different dimensions, but one of the things we did was we took cognizance of this increasing gap between the performance of disk and DRAM, which, as we can see, just kind of go along here on flat red lines over the years, and the increasing speed of processors. So, if you look at those green bubbles, those show that processors get faster every, they get how fast? Twice as fast every 18 months, basically, is what Moore's Law has turned into. Now, sort of down at the end of that line, processor frequencies actually stopped going up and people started making multi-cores, but you kind of got the same effect. You got twice as many flops for the dollar every 18 months. But you didn't get twice as many I/O ops, and you didn't get twice as much memory capacity every 18 months. And you started to develop very imbalanced systems that could really not run at a large fraction of their peak. We decided to do something about that. One of the things we decided to do, so it's called a latency gap. If you look at how fast can you do a floating point operation today? Any thoughts on that? Any processor could do 1 billion floating point operations per second because it's got a gigahertz clock, right? And a giga is 1 billion. But most of them do multiple. In fact, a Sandy Bridge processor, which we have, and I'm not even supposed to say exactly what it can do, but roughly we're talking about a 3 megahertz clock, so 3 billion times a multi-way issue. So 3 times 8 or 16 just per processor. So it's a massive amount of flops, and it can do that multiple per cycle. How long does it take it to access memory? 100 cycles. God forbid that your program should do one data access to main memory every several hundred flops because you just won't get the peak. And if you go out to disk, you're dead. It's 10 million cycles out to disk. Into that gap, which we call the latency gap, we stuffed flash disks that are not as fast as DRAM, but are much, much faster than spinning disk. And basically, we moved off of spinning disk as our primary place to access data. We still have it as archive or as backup. But while the application is running, it's just going to go to spinning disk. And that's going to make you 10 or 100 times faster on the I/O portion. If your application is mostly I/O bound, it's going to be 10 or 100 times faster. If it use Amdahl's law. If it's only 50%, then it's going to just speed up that portion. But it can be dramatic. Now, I think there's some questions that you're going to be asked to be entered into the raffle as we go along, and so I'm throwing out some facts. You know, pay attention to the facts. One fact is that when we first proposed this, people said, you guys are nuts. You can't build a supercomputer based on a flash disk because flash disks wear out. Who would, you know, you'll wear it out and it won't be useful. Well, couple of interesting facts. What's the lifetime of how long is a supercomputer relevant? You know, a supercomputer comes along and it appears in the top 500 list, you know, maybe high up in the top 500 list, like Gordon is sitting at number 48. How long does it stay there? Well, it plummets rapidly through the disk by Moore's law, and the basic rule of thumb is after 2 turns of Moore's law, it's fallen way down the list. So that's only 3 years. You know, in 3 years you will see it rapidly. 3 years there will be 6 lists, and it'll start at the top and trickle to the bottom. We normally retire systems after about 3, 4. Sometimes you can squeeze a 4th year out. Completely relevant question. How long would an SSD last if you just wrote to it all the time at peak rate while processing your workload? We did the math. Turned out with new wear leveling technologies and over provisioning, it's about 3 years. When we did that math, we're like, maybe we're onto something here. What if we just stand this thing up, populate it with flash, pound the heck out of them, and either the system will be retired after 3 years, or if it's wildly popular, then we'll just have to reprovision the flash disk at that point. And so that was how we got around that. And you know, when we were looking at this stuff 2 years ago, or 3 years ago, 2.5 years ago, this was kind of highly controversial, but now it's much more common, and you see flash more, but not as much as we have. So we have about 320 terabytes of disk, a flash disk. And as I mentioned, we can achieve 35,000 I/O ops per disk, which turns into 35 million I/O ops total. Gordon is based on the Sandy Bridge processors, the Romleys, which just came out. What we're seeing out of them is really awesome. If you go and look at the top 500 list, what you'll see is that we're only 48, but we're doing it with half the number of cores of other systems in the same region. So the flops per Sandy Bridge is really high. You get fewer nodes. You don't have to scale as far. You get great I/O ops performance. And of course, this is all low-level benchmarks. We are looking forward now, and we've along the way we built a 3D torus out of IB, which hadn't been done before at this scale. Appro stepped up to all these challenges. Another interesting fact is, when we came up with this design, we went around to all the big companies and asked them if they could build this for us, and they told us to get lost. I'm not going to mention any names, but one company told us, for $20 million, we cannot deviate from our product line, and we will not. You could buy what we're going to offer you in that time frame, or take a hike. So we took a hike over to Appro, talked to Appro, and Appro said, we'll try it. You know, we'll go out on a limb here. We'll try to build something innovative and unique, both architecturally and use the SSDs. Today, that's looking like a smart thing to do. You know, we've created a system that has some unique capability. Of course, where the pedal hits the metal is, what are we going to be able to do with this thing for real applications, right? It's great to have flops. It's great to have I/O ops. We're looking at a range of interesting ones. I'm going to just show you a couple of early results that came from our prototype system that we built. We have radar analysis type codes, we have social network type analysis codes, and of course various kinds of engineering codes that are substantially accelerated by running from the flash memory versus the disk. And you can see here we're getting, you know, 2 to 4 times speed up. It's not 10 or 100, but you know, on a real app that is doing some I/O, and we get substantial increases. And the other piece of technology that I just wanted to tout a little bit was this great software from ScaleMP that takes multiple of these Sandy Bridge nodes and puts them under one big shared memory. So we can take 32 Sandy Bridges, each with 64 gigabytes of memory each, put them all under a shared virtual memory that its purpose is not to share with other applications. It's for your application to be able to see all this memory as one cache-coherent shared memory. So you can get 2 terabytes of cache-coherent shared memory for a data-intensive or like OpenMP type parallel code. And we've got some codes in genomics that are running really well under that environment. And they're nearly beating, or they're hardly slower than SGI hardware. You know, I love SGI. Sorry, you SGI guys, but SGI has spent a huge amount of money and gone bankrupt twice building hardware support for cache coherent shared memory. But this is in software. It's cheaper. It's nearly as effective. And once you throw in the Sandy bridge, it may exceed it. So anyway, that's a bunch of facts, a bunch of information about Gordon. Hope you enjoyed it, and I don't know if you have any questions.